he's a little bit more specific. He's like, it's V that is a mapping from I to the tangent space of Rn, given by T maps to V of T, all right, which is an element, more specifically, of the tangent space at C of T of Rn. That is just a fancy way of saying it is attached to the curve at the appropriate point, right? Now, you can define a now, this, there are two ways you could think about this. You could think, well, where's this vector field coming from, right? It's coming, maybe it could be coming from a vector field which fills all of space, right? For example, you could think about the vector field that fills this room with gradients for the temperature function, right? You pick a point in this room, that gradient vector points in the direction of increasing temperature. Well, if I take this room and I just look at the front desk, I can look at the restriction of the gradient vector field just to the surface of this desk, right? Desks. And that would give me a vector field on the desks, right? Formed by restriction of the larger vector field. Well, we could think about vector fields that are formed by restriction, but we can also think about vector fields which don't really exist in the larger context, which just exist along the curve. The principal one that you think about would be the tangent curve, right? So the tangent curve, C dot, he uses dots here, C dot of T would be the sum, I equals 1 to n, of dci dt partial xi. So this is the velocity vector field. I usually call this the tangent vector field, to see. Yeah.
If you took the restriction of the temperature gradient vector field to the desk, like you were saying, then it wouldn't be a vector field on the desk if we thought the desk is a manifold, because it's not, because some of the vectors might be pointing non-tangentially.
That's a good point. Yeah, that would not be a vector field to the desk as viewed as a manifold. I mean, it would not be a tangent vector field, not without some other procedure, namely projection, right? And to do that really is where you get into the connection. The issue of connection and projection these are sort of two sides of the same. Again, we're taking an extrinsic viewpoint, so I can't say too much because we really want the connection idea to be an intrinsic thing, just based on the given metric for the space, not on how we restricted the space from a larger ambient context. Okay, anyway, so there's your velocity vector field. And he says, at this point, it's not hard to see that the definition of covariant derivative, nabla xy, extends directly to vector fields along a curve. So in particular, we define the derivative of a vector field V along a curve C as follows. Oh, if we need those formulas, I'm going to regret what I just did, because that was like a solid 5 minutes of writing right there. So here's the definition. D, V, big D, not a typo, little dt, weird notation, right? This is nabla C dot of T, V. Let me put it in words again. This is the derivative of vector field V along C. So what this does, and now of course, if you just let's see here. If we're just working in in flat space. If we're just working in like, Euclidean 3 space or whatever, this is not, I suppose, that interesting. This becomes more interesting when you think about the curve being on a curved space, right? And we're measuring the rate of change and that V is a vector field, which is on the, like you said, it's tangent to the surface, and this is going to measure the change in V, that V on the change in the vector field on the surface as it goes along the curve, right? Let me just uglify things here momentarily. He thinks it's worthwhile to write the formula here, and I think he's probably right. So what this actually means in coordinates is as follows. dv dt is equal to the sum, k equals 1 to n, of d vk dt plus the sum over I and j of gamma ijk dc I dt v upper. He can't. He's got the lower index on the tangent curve, but he's got the upper index on the v. It kind of cracks me up. Anyway, so man after my own heart. Let's see here. He believes in using all notational schemes at the same time. In the interest of confusing the students maximally, I like it. I like it. So you see that this dv dt, it gets married to the connection coefficients. It involves somehow the curvature of a surface, right? Definition. If we have V, a vector field, along a curve, C, all right, again, parameterized curve, and he's still in domains, whatever, then V is parallel. What would it mean for a V to be parallel? Is 0. That is exactly it. Yep. I'm just recording the definition here again, obviously. So if you looked, for a given curve, the condition, just look at this. If the curve is given, right, and you want to go searching for vector fields which are parallel to the curve, what does that mean mathematically? What are you trying to do? Trying to set this equal to 0, which means you got to solve for what? You've got a differential equation, first order differential equation in V's with these, whatever happens here appearing as, and what I just erased shows you that these differential equations could be rather challenging, right? They can be nonlinear and quite ugly. But, so, great. You got an example, though, that makes you feel better about your life. He's like R2 with G ij equal to delta I, R2 Euclidean R2, the standard Euclidean metric, then of course we have gamma ijk equals to 0. It's like half of my examples are this, right? And so if you're looking for a vector field which is parallel to a curve, what are you trying to solve then? I'm sorry, there's something, I'm missing something here. Where is this? There's no, oh, that's the interesting thing. Look at that. Oh, cool. Look at that. That's actually kind of the point, isn't it? I'm like, but he didn't give me a curve. He didn't give me a, I'm like, I'm missing, I'm looking. Where's the curve? Where's the curve? Why doesn't it matter? Right, these are gone. So the condition, like the search for parallel vector fields just becomes the search for solving these. Well, dv1 dt equals to 0, and dv2 dt equals to 0, which even in my current state I can solve. v1, so I mean here, v is equal to, v1, v2, constant, right? It's a constant vector field. It literally is a constant vector field. Which of course is what, I mean, that's our usual usage, right? I don't care what kind of curve I have, right? If I have a constant vector field along the curve, what that means, of course, is that this is that thing we do in physics, right? And now we're starting to get very close to being able to define parallel transport for, something other than this case. But example 5.43 is a little bit more exciting. He talks about the Poincare metric, right? Here we have the matrix of the metric is 1 over y squared, 0, 0, 1 over y squared. And whew, goodness gracious. Well, I'm not even going to write it down. It's quite complicated, the conditions for a parallel vector field to the Poincare metric. They're ugly. If you look on page 227, they're written. And he mentions if you fix the curve to be the horizontal line segment, which is parametrized, if you look at, so page 227, I'll record one of the results for the sake of our discussion here. For this curve, c of t equals to t1, right? 0 less than or equal to t less than or equal to 2 pi. The vector field v, which is, what's the word? Constant along that path in the sense that we just defined, is this cosine of t partial x plus sine of t partial y. Now that's a little bit weird, isn't it? Given our usual understanding of what constant means. But keep in mind, we're talking about the upper, so here's 0. This is t equals 0 here, right? And over here is t equals 2 pi, let's say. And he's drawn some arrows in the picture. He actually showed, you can visualize it. It's something like, I'm doing it wrong. Anyway, you got the idea. It ends up like this, but that's a constant vector field with respect to the Poincare metric for that horizontal line segment. So that seems a little bit off, doesn't it? What does that mean? You know? What does that mean? Proposition 5.44 says that if we have a Riemannian space with connection, Riemannian connection nabla, and if V is parallel to curve C, all right, then V has constant magnitude along C. All right. I'll go over the proof of that next time. Proposition 5.45 says that if you've got V and W parallel to C, again in the context of a Riemannian connection in a Riemannian space, then the angle, the G angle between V and W is constant. So if we look at constant vector fields along a given curve, they have constant magnitude, and if you've got a pair of them, the angle between them at one point is the same as the angle between them anywhere else. What does this mean then? What can you use? What does this suggest? Well, theorem, I'll read it, I won't write it down at the moment, but theorem 5.46 says this: if you have a Riemannian space with a corresponding Riemannian connection nabla, you've got a smooth curve P, and if you have a vector V naught in the tangent space at P, then there is a unique parallel vector field which starts at V naught and is constant along the curve. So these theorems make it possible, because it basically says if you've got a constant vector field along the curve, it's constant magnitude, right? And if you got two of them, it has an angle which is fixed. So if you start out, if you start out like this, and you get a constant vector field, it has to somehow maintain the. Again, what that means is not obvious in weird metrics. What it means to parallel transport is not always intuitive. And that brings us to our final definition for today. It's if we have U and G Riemannian space, all right, with adapted, as he says, he calls it the adapted Riemannian connection. In other words, it's nabla as we've built it, okay? Then a parametrized curve C is a geodesic if the covariant derivative along the tangent field with respect to the tangent field is 0. Or in the big D notation, that's saying that d of c dot dt is equal to 0. And you start to be close to understanding why geodesics are curves with 0 acceleration. as it's understood with respect to the geometry here. The notation is trying to make you think that, right? It's like it's zero acceleration curve with respect to the geometry. But this is the condition for geodesic. And then you can prove that these give you paths of shortest distance between 2 points. Possibly. I mean, you got to be careful. If you're on a sphere, right, and you pick 2 points and you look at a geodesic, there's a great circle, right? So if you go the wrong way, it's not the shortest distance. But if you go the right way, it's the shortest distance. But anyway. So next time, we'll continue talking about parallelism, this idea of parallel transport and what it does for us. And that leads us naturally to the section after that, which is curvature. Curvature is something awful, even more awful than this, that you can do, combining these things to make something else. And when that something else is non-zero, it detects the space not being flat. It detects non-zero curvature means that the space is actually curved in a technical sense, in the sense that the intrinsic geometry of the space is non-Euclidean. For example, a cylinder will have zero curvature, but a sphere will not. So curvature will not pick up on global topology. It's true that in a cylinder, eventually you'll figure out you're in a cylinder, right? When you go back and keep going and you come back to where you started, you'll notice that you're in a cylinder, right?
But the geodesics work just like they would if you unwrapped it.
Yeah, exactly. It's still straight lines, essentially. And if you were living on the cylinder, you couldn't tell.
So a cone would not have zero.
A cone is actually another one with zero curvature.
Right, because again, you could
Except at the...
Like the final point.
yeah. But a sphere, if you were to set up a triangle, you could measure the difference in angle versus Euclidean geometry. So those kinds of issues eventually get brought up in the discussion of curvature, which is a harder thing. And it's still very much an open question, exactly the connection between curvature and topology. That's a deeper thing. We have many results, but many open questions as well. So I'm going to stop it here today because I have to go pack up. So sorry to deprive you of your final extra 10 minutes of class. Thanks, Travis.